Welcome back to the Info Engineer Explainer. Today, we're tearing down the wall between textbook electrical theory and actual, boots-on-the-ground field reality. If you've ever stared at a schematic and wondered exactly how that translates into a massive, functioning commercial site, well, you are in the exact right place. We're skipping the fluff today and diving straight into the technical depth of real-world site electrification.
Think about this number for a second. Less than 3 months. That right there is the payback period for a properly engineered automated capacitor bank. For industrial facilities getting hammered by heavy inductive loads, this isn't just a neat electrical upgrade. It is a massive financial solution that stops utility penalties completely dead in their tracks. We're going to break down the exact math on how that works in just a minute.
Here's our blueprint for today. We'll be hitting project management, power factor economics, earthing system design, advanced arc fault protection, solar site electrification, and we'll wrap it all up with the project feasibility summary.
Section 1. Mastering Project Management, from tender all the way to handover.
Look, you don't just roll up to a site with a toolbox and start pulling wire. A real-world project has a strict sequential flow. You start by analyzing the initial contract docs and tender drawings. Then, you move into detailed design and finalizing your bill of quantities, or BOQ. From there, procurement steps in. You finalize vendors, and you hold a formal kickoff meeting to lock in mobilization and safety plans. And finally, after the installation is done, you enter the strict handover phase, passing over operations manuals and, crucially, your as-built drawings.
And that brings us to a really critical distinction. We have to separate the pros from the amateurs. Professional execution is driven by rigorous documentation, detailed single-line diagrams, quality plans, neatly labeled wire diagrams inside your distribution boards. If your site is characterized by chaotic panels and zero as-built drawings, you aren't delivering an engineering solution. Honestly, you're just engaged in a really expensive, dangerous hobby.
Section 2. Power Factor Economics and Automating Reactive Power Compensation.
Now, to really get the economics, you got to grasp the physics first. When inductive loads, like large motors or transformers, run, they cause your current to lag behind your voltage. This means your facility sucks down excess reactive power. It doesn't actually perform any real work, but it completely chokes your system capacity with higher current flow and I²R losses. And utilities absolutely hate this. Local distribution companies, your DISCOs, will slap massive financial penalties on your industrial site for any power factor that drops below their minimum threshold. So, what's the fix? Microcontroller-driven capacitor banks. We aren't talking about static capacitors that just sit there and can't adapt to changing loads. These automated systems monitor the phase angle in real time. The second your power factor drops, the microcontroller dynamically injects leading reactive power by switching those capacitors on, which perfectly compensates for that inductive lag on the fly.
The math literally speaks for itself here, and this is drawn directly from a real-world case study. By bumping up a lagging 0.72 power factor to a highly efficient 0.97, an annual 20,000 pkr penalty from the DISCO was completely wiped out. And because the hardware cost for the prototype sensors, relays, and capacitors is so incredibly low, it pays for itself in under 3 months. This is the exact definition of high ROI engineering.
Section 3. Designing earthing systems for high-rise and commercial builds. Depending on your soil resistivity test results, you've got a few options for grounding. For large commercial sites, you're usually deploying a massive bare copper grid under the building for uniform potential. Need to hit the water table? You drive copper-bonded steel vertical rods deep into the earth. But what if you're building in a bone-dry desert environment? That's where you deploy UFR grounding. This is a brilliant, concrete-encased method invented during World War II for bomb storage vaults. It uses the naturally high pH and moisture retention of concrete to give you an incredibly low-resistance path to ground, even when the dirt around it is completely dry.
And please never just guess your wire size. To size the buried copper conductor for your grid, you calculate it exactly. Say you have a maximum fault current of 20 kiloamps that needs to clear in 1 second. You apply the standard formula using a material constant of 115 for bare copper. That gives you a base of 174 square milliliters. Then, you always add a safety factor of 1.25, which brings us to 217.5. You can't just buy that exact size off the shelf, so you step up to the industry standard 240 square millimeter bare copper cable. That is how you engineer for absolute safety.
Section 4. Advanced arc fault protection and mitigating fire risks.
So, a tiny loose connection can cause a very dangerous electrical arc. The problem is, conventional breakers will completely miss the characteristic high-frequency patterns of these faults, but modern devices like the Eaton AFDD Plus use highly sensitive electronics to actively monitor the installation. They identify and shut down these hidden dangerous sparks long before they can start a fire.
But what makes these devices truly pro-grade are the built-in diagnostics. It's a massive time saver for engineers in the field. Just by reading the specific LED flash sequences on the device after a trip, you can decode exactly what went wrong. The device actually tells you if it tripped because of a serial arc from a damaged wire, a parallel arc between line and neutral, or even if the mains overvoltage spiked past a dangerous 270 volts AC. It totally eliminates the guesswork from your troubleshooting.
Section 5. Solar Site Electrification and Balance of System Engineering. A solid off-grid solar setup is so much more than just slapping panels on a roof. It requires meticulous balance of system, or BOS engineering. Sure, you have your PV panels and your battery bank, but you must integrate a charge controller to manage the flow. You need proper fuses and breakers to hit NEC overcurrent protection standards. And crucially, you have to precisely calculate wire sizes against the total load distance. If you fail to account for long cable runs, you are going to suffer hazardous voltage drops that will completely cripple your system's efficiency.
And speaking of efficiency, here's a massive factor for solar economics. The absolute secret to preserving your wildly expensive battery bank is strict depth of discharge, or DoD management. Listen, if you drain your batteries completely flat every single night, you will destroy them. By engineering your storage capacity so you're only cycling between 10 to 60% of their capacity daily, you will drastically extend their operational lifespan.
Finally, Section 6, our project feasibility summary, the engineer's final briefing.
This feasibility matrix really drives the whole explainer home. If you want the absolute highest financial ROI, automated power factor correction projects deliver incredible returns by wiping out those disco penalty bills, even though they are highly difficult to implement. Solar site lighting gives you a medium ROI through fuel savings. And rigorous earth grid designs? They might not generate immediate cash, but their ROI is listed here as critical because they are absolutely non-negotiable for site safety and standard compliance.
So, the next time you're staring down a set of facility drawings for a site electrification, ask yourself, are you actually applying meticulous engineering standards? Are you calculating exact wire sizes, managing depth of discharge, and automating power correction? Or are you just settling for an expensive, dangerous hobby? Bridging the gap between textbook theory and field reality takes discipline, but the financial and safety payoffs are absolutely massive. Keep engineering, stay rigorous, and I'll catch you in the next explainer.